which is basically a two-dimensional surface. What about inside? The theory is that the universe is still expanding, and it's expanding everywhere at once. Jeff, do you have any clarification on that?
Yeah, I've done that before.
Yeah, okay. Here's the expert.
No. In the balloon analogy, okay, so I don't have a balloon with me, but what you do is you take a balloon and draw new galaxies on the outside, and then you deflate the balloon. As you inflate the balloon, you watch as the balloon inflates, the little galaxies you want to move apart. The assumption here that you have to remember is that you're simplifying the universe. You're not saying that the interior of the balloon is part of the universe. Pretend the universe is just the surface of the balloon. The surface of the balloon has no center. So you have to kind of ignore the inside of the balloon. I know you're simplifying things, taking out a dimension. But as the balloon expands, in that sense, the balloon surface is like space itself. So you're talking about the surface of the balloon. That's how that analogy works. It's not a good one. Space is not curved like a balloon, but it shows you that as the balloon expands, if the surface of the balloon is analogous to space expanding, the galaxies move apart. So that's kind of how that works. We have some stretchy fabric or something like that that's a little bit better analogy, but you can't imagine in all these dimensions, you can't come up with an example, so that's a good simplification of it. And what was your other question about?
You said 380,000 years ago back.
Oh, okay. Yeah, okay, so the universe was once smaller than an atom, hotter than the sun. It expanded, and as it expanded, it cooled. Things that expand cool. That's how your refrigerators work at home. Gas expands, it cools. The same thing with the universe. After about 3 minutes, the universe had expanded enough so that atoms could form. Not neutral atoms, but the helium nuclei. And then the universe continued to expand. And after about 370,000, 380,000 years, before that time, the universe was just a soup of matter and energy. What I mean is that matter and energy really couldn't be separated. If you had a photon of light, it wouldn't travel very far before it ran into some matter, got absorbed, re-emitted, absorbed, re-emitted. You couldn't travel unimpeded through the universe. After about 370,000 years, the universe had cooled enough so that neutral atoms could form. Electrons and the nuclei, the neutral atoms, that made the universe turn transparent. Suddenly, a photon of light emitted could travel relatively unimpeded through the universe, and these photons are still traveling today. Those photons that, when the universe went from opaque to transparent, when neutral atoms formed, it's called recombination. Those photons of light are still traveling today. That's what we call the cosmic microwave background. Those photons are everywhere. They're in this room. You look at the tip of your pinky, about 1 cubic centimeter. There's roughly 400 of those photons right now at the tip of your pinky. It's everywhere. It's relative radiation that was emitted 370,000 years after the Big Bang expansion. Does that kind of help?
There are more questions now than ever. Yes.
Could you come up with another descriptive term to replace Big Bang so that we can kind of wrap our heads around?
I thought we'd been through that.
But I don't understand.
A better term than the Big Bang. Wow. Yeah, we can have another contest. We'll wade through another 13,000 submissions.
Wasn't it the writer Douglas Adams who said that there's a species who claimed that the universe was sneezed out of the nose of a being called the Great Green Harple Seizure?
The Great Green Harple Seizure, yeah. Yeah. Yes.
Yeah, no one's really mentioned is the expansion that's occurred. Can you comment on that? Is that still something we can think about?
Re-expansion.
So the expansion that early that happened.
How did it happen? What started it?
It didn't appear anywhere, and I'm wondering, do people still believe it? And what does it really mean?
That's something, well, what is the mechanism that started the expansion? Would you like a Nobel Prize? I don't think anybody can answer that.
I can.
You can try. There you go.
I'm not an expert on this, but the physicists claim that it's a field called they call it the photon field, and that at some point this field made an energy changing state that caused the expansion of the universe. And how it happens seems to be a quantum mechanical effect, a tunneling type effect. That's what they say. No one really knows. And like Bing said, whoever figures it out and proves it will be the Nobel Prize.
Maybe take a break.
I'll have
Break? One more question, then a break. Oh, well, I already picked him out. All right, 2 questions.
So I'm having trouble with this expanding universe notion. What are we expanding into?
What are we expanding into? That's an interesting question. One answer that cosmologists give is the universe is creating the space into which it's expanding. Steve.
No, Brian.
Here's a question. Based on the film that we're going to have showing, are there 10 to 25 questions that you will come up with that we will have answers to with reference to this film?
Is there a standard set of questions that we are going to give to you that we expect to be commonly asked? Yes, we have an FAQ about cosmology that's been put out, and we expect this to develop further. So it'll be a living document. We'll add questions to it as we get them, and we expect a lot of interesting questions. We expect some answers, and we expect to be challenged on the material of the show, quite frankly. So it'll be interesting for us to see how people respond to this presentation. Okay.
I'll jump in on that one also.
Yeah.
So the pricing questions is actually one of the files that went out. It's 3 or 4 pages of a lot of the questions that we'll be seeing. So I know a lot of people weren't able to open that, and again, I will be sending that out to everybody in a format that's more accessible. But it sounds like, well, first of all, I'd like to say thank you, Bing. That was actually all right, so yeah, I don't want to keep you guys too late, so I don't take too long on this. So what I want to do is just go through a really brief overview of spectroscopy. Some of this will overlap with what Bing said, and I'd like to take questions, but I think we need to hold them till the end because I really do need to get through with this. But in essence, most of what we know about the universe, most of it comes from studying light. Other than our solar system, we can't send our robotic explorers, we can't send human explorers. Most of what we know about the universe we have to get indirectly, and that comes by teasing out details from light. And studying the spectrum of light is an essential part of that, an essential part of how we understand our universe, what it's made of, and basically what it's doing. In a sense, I want to first just kind of go through a really quick overview here. We're going to be looking at an electromagnetic spectrum in a moment. By the way, this goes with Henry's document. So if you're following along, you probably see these, at least some of these images in Henry's document. Electromagnetic radiation means light. It's the same thing. Light can be thought of as both of a wave up here with a peak and a trough and a wavelength. But you could also talk about light as a particle. It all depends on how you're doing the experiment, who's setting it up, whether light behaves as a wave or a particle. It's one of those strange things of nature. It's called the wave-particle duality. So sometimes I'll be talking about light as a wave, sometimes as a particle or photon, and it behaves as either, depending on what kind of experiment you do. So in terms of wavelength, we, as you learned from Bing, long wavelength light is low energy light. So if you have a long wavelength, you have very low energy light, infrared, radio. You have short wavelength, high frequency light. I shouldn't introduce frequency, but wavelength and frequency are inverses of each other. So if you have a short wavelength light, that is high energy light, ultraviolet, X-rays, gamma rays, things like that. Oh, I did want to talk about this really briefly. In the spectroscopy lab, what we're going to be doing are using little gas tubes, which you'll see down here. These gas tubes, we run an electric current through these gas tubes, and we look at the light from those gas tubes. And as being explained earlier, the light that elements give off Remember he had those little diagrams that showed the lines, whether they're emission or absorption lines. The lights that they give off are the key fingerprints that we can identify the elements from. We do this in labs, we do this in all kinds of sciences, chemistry, biology. Well, we do this in space as well. The essential way that this works is, if this is an atom, this is just a diagrammatic thing. If you have an atom, and you might pretend that these are two energy states of an electron, you have a low energy state and a high energy state of an electron. Well, an electron at a high energy state, such as this, that electron will spontaneously fall down to a low energy state if it can. That difference in energy, as the electron changes states from one orbital to the next, that difference in energy kicks off a photon of light of exactly that energy. This is a very simplified diagram, but the difference in potential, the difference in energy between these levels as one electron falls down to the other tells you exactly the energy of the light, exactly what wavelength, what color that light should be. So these differences depend on the atom. These are very well known from quantum mechanics, what these changes in energy levels will be. So we know exactly what light should be given off, and we can confirm that in the lab, and then we can look for that elsewhere in the universe. Okay, so Bing talked about various examples through history. He talked about Newton, and he talked about Herschel and their experiments with prisms, breaking up white light into its constituent colors. Now, white light, or visible light, is just one little part of the electromagnetic spectrum, or all of light. It's all light, whether it's radio waves or gamma rays, that's all light or visible light, but we only see a little tiny sliver of that. What we're using is something called a diffraction grating. It works just like a prism, but it's more precise, and this is what scientists use. In our little box, we will have a little slit which light can come through, and I'm not sure how this diagram works very well, but light comes through this little slit, and this image doesn't make a lot of sense to me, but the diffraction grating breaks up the light into its constituent colors, which you can observe with your eye, or you could use digital detectors like they do in astronomy. What you're going to get out of it from these gas tubes that glow because we're running an electric current through it, that electric current excites the atom, kicks up the electron into a higher orbital, that electric current that goes through the tube, so it kicks up the electron into a higher orbital, and when that electron spontaneously comes down in energy, it's going to kick off a photon of light, and that's the light we're going to see from the tubes. So we're going to see these emission line spectra. Okay, so this is what we're looking for, and from the emission lines that come off, we'll be able to identify what element it is. As astronomers look out in the universe, they can find various elements, various compounds. It's very sophisticated these days. Sometimes, though, you'll see what's called a continuous spectrum, which is a spectrum that hot things give off. You heat up something very hot, like a star or the filament of an incandescent bulb, you get a continuous spectrum. And then you often see these dark lines in this continuous spectrum. These are absorption lines. This is not where the gas is emitting a line because it's dropping an electron in its orbital and then kicking off a certain energy of light. This is where it's absorbing that, and it's, so the electron will get kicked up and the atom will absorb the light. So sometimes you see absorption lines. We're not going to do that in the lab. We're only going to do emission line spectra. So as I mentioned, it's used in all kinds of sciences and to tell what something is made of. You can do it in chemistry, biology, and when we look out in the universe, we can compare what we see in the lab with what we observe in the universe to identify elements. In fact, helium was first detected on the sun before it was found in the laboratory, just by its spectral lines. And we're finding all kinds of crazy molecules in space with better spectrographs and much better computing power. It's amazing the complex molecules they're finding these days. So, expansion of the universe. How does this all tie in? Well, this is kind of slightly different and not definitely related to your lab, but Bing talked a little bit about the Doppler effect. An object moving towards something will shorten that wavelength or increase its frequency. So if an object is moving toward you and it's emitting light or even sound, that's going to be shifted toward a higher energy state if it's moving toward you. If it's moving away from you, the wavelength that gets stretched out, the energy of the light will become decreased. And this is true with light, but you have to move at very fast speeds to make it very noticeable. Though they're getting incredibly good with these detectors these days, that they can measure stars that are moving, about the speed that I'm walking across this room, quarter away from you. So they're getting incredibly sensitive with these detectors. But the universe as a whole is expanding. Let's see. Some of the, back up 50 years ago, there was an object that was found by Martin, well, it was actually found by Martin Schmidt, but he studied it. It's called a quasar. This one was, I think, 3C273. It was the first identified quasar. And I have an image here, so let me pull this up that I wanted to show you. So this is almost 51 years ago when Martin Schmidt first found this. And I think I can enlarge it. Maybe there's a full screen button. I'll just enlarge it. There we go. So this is Martin Schmidt's first actual image. So this is the way they used to do it. So photographic emulsion, and they would split it up with a diffraction grating. And this is what Martin Schmidt observed. He saw these lines. No one could identify what the lines were. They didn't make any sense to anyone because no one was expecting these lines to change significantly. But remember, the Doppler effect, and there's another type of effect, which this turned out to be actually, can shift those lines. And this is a laboratory spectrum. Okay, so this is your comparison spectrum from the laboratory. And when you take your observation of 3C273 and you line it up, you see that these lines do line up if you shift them. So this is your H beta here, and here's H beta in the observed spectrum. Everything's shifted by about 16%. So what does that mean? Well, when something is shifted that much, it is shifted actually towards the red part of the spectrum. So the light is losing energy. There's two ways to interpret this. There's actually three ways, but two main ways. And Bing talked about one of them. This object could be rushing away from us very, very fast. Or there's something else that can cause light to shift. And that is the expansion of the universe itself. And I don't have the movie, it wouldn't play, but we're I'm going to send you to the Hofeld Hall whenever you get a chance to see our Ancient Light show, which talks about the universe expanding. And the expansion of space itself will actually stretch light. And it looks identical to a Doppler redshift, a Doppler stretching of light due to relative motion, but it's a little different. A very distant object that emits light from very distant from you, as that light is traveling to over perhaps billions of years, as space is expanding in an expanding universe, well, light stretches along with the expansion of space. Does that make sense? It's called a cosmological redshift. To the observer, it looks just like a Doppler shift, but it's a different cause. Okay, so Schmidt had to figure out 50 years ago, is this a Doppler shift or is it a cosmological redshift? He figured it didn't make sense for it to be a nearby object with a high speed because that speed would be 16% the speed of light or something like that, something crazy. He said it has to be a distant object with this light stretched by the expansion of the universe. And so some of the most distant objects we know today are these quasars. And we found millions of them so far. These are the ultra-bright cores of very ancient galaxies. Where supermassive black holes are feeding on the abundant gas and dust in the early universe. It's abundant gas, I should say. So this all gets us to the most ancient light in the universe, the cosmic microwave background. This is light that has been stretched, not by a Doppler shift, but by the expansion of the universe itself. How much? They say it's got a Z of about 1,000 or so. It's been stretched all the way from visible light. So when this light was emitted, the universe would have been awash in a glow of visible light. But it's been stretched all the way through infrared and into the microwave part of the spectrum. It's been stretched incredibly, by a factor of 1,000 or so, over 13.8 billion years of expansion of the universe. It's everywhere we look in the universe. It's almost completely uniform, but there are some minute variations that are amplified here. What they show, Bing talked about it as temperature differentials, but I like to think of them, the red regions are the less dense regions, the blue regions are more dense regions. They're only different by roughly a part in 100,000, not much difference in density. But something amplified those differences. That's primarily that the denser regions became denser because they contain more material, more gravity, and gravity has pulled the dense regions together, even while the universe as a whole is expanding. So the less dense regions, the redder regions, became these big voids, and the blue regions, the more dense regions, became the filaments and superclusters of galaxies. The denser regions became denser, the less dense regions became less dense, creating that filament-type structure you see today. All right, that's it in a nutshell. I didn't want to talk too much. I might have time for a question, or do we need to move on?
So, yeah, we abbreviated it because Ben covered some of the things.
So because I went so fast and didn't explain things very well, I'll take a couple questions, but I don't want to keep you guys very long. So, yeah, go ahead.
Does the percent shift correlate with a percent of light speed?
Does a percent shift correlate with the percent of light speed?
12%.
If it's a Doppler shift, yes, you can calculate how fast it's moving away from us. But if it's cosmological redshift, the light is stretching with the universe itself. So as space itself is expanding, it's stretching the light with it. Yes, you could calculate how fast that object is probably moving away from us today based on what we know about the expansion of the universe. I guess this is how to think about it. So let's say 13 billion years ago, a galaxy emitted some light toward us, okay? The universe was much smaller 13 billion years ago, very small, and not expanding nearly as quickly because we were much closer together. So that light has been traveling toward us for 13 billion years, trying to cover the distance. Meanwhile, space between it is expanding, so it takes longer to get to us. When it finally gets to us, it's not telling us what that object is doing now. It's telling us what it was doing 13.8 billion years ago. So at this time, it would be an object that would be rushing away from us extremely fast, but that's not what the light is telling us directly. The light is just telling us that this is what I was like when I was emitted 13 billion years ago, but I've been stretched by the expansion of the universe. So it's telling us how fast the universe is expanding, which would tell us, yes, how fast it is rushing away from us. Yeah, it's a heady kind of thing. Yeah. Question?
When Higgs said that 3/4 of the universe is dark energy,
yes.
Are the black holes in the gas?
So the question is, 3/4 of the universe is dark energy. Yes, this is including black holes. Yeah, dark energy is not something. Dark energy seems to be a feature of space, but dark energy, we don't know what it is exactly. But when they're adding up all of the universe, they're adding up black holes too. Yes.
Okay, and the other one was does the string theory relate to the expansion of the universe?
Does string theory relate to the expansion of the universe?
Yes.
It does, but string theory doesn't really make any predictions about the universe that I'm aware of. It's more of an explanation, possibly in mathematics, how this could all fit together, but it doesn't seem to make any predictions about whether the universe would expand or not. Yeah.
Does hydrogen have 3 bands because the electron could have 3 different energy states?
Hydrogen has more than 3 bands. And that, I think, has to do with molecular hydrogen. I'm not exactly sure, but there are more than 3 bands. There's what's called the Balmer series and the Lyman series of bands. The Lyman series are in the ultraviolet. I'm not exactly sure what causes that, but certainly there are a lot more than 3 bands in hydrogen. You can have ultraviolet light that is emitted by something very far off in the universe. By the time it gets to you, it might have fallen into the visible range. This would be one effect of redshifting. This is one of the reasons why the big telescopes that we're building right now and the telescopes we're launching into space are primarily going to be looking for infrared light, because when you're looking at very distant objects from the very beginning, when things first started to form a few 100 million years after the Big Bang, the light will have been stretched from optical into the infrared part of the spectrum.
Just a comment, you said hydrogen H2 in the...
Hydrogen H2, that would be...
cells.
This should be... this should be...
Hydrogen's not in there.
Is it H2 in the tubes? It should be H2 in the tubes, but once the current is flowing through, when the current's flowing through, is it still H2?
I would think so.
Does anyone have a physics degree here?
There's enough energy in there so that you're going to ionize.
You should ionize it. Yeah, it should become atomic hydrogen.
The molecular forces are very small. So you're going to break the molecules apart. And then you're going to ionize the single atoms, which is what's going to give you the
Are you hearing it? Okay, this meshes with everything I was told, but I didn't want to go beyond my expertise. I don't have a degree in physics, but yes, this when the current is flowing through it, it will ionize the hydrogen, so it will become atomic hydrogen, and it will strip off the electrons
it'll strip the electron off, and then it'll fall through those molecules.
and then when it recombines, recombine with an atomic nucleus, and then it'll fall down through various energy states. And at each discrete energy state, as it falls down, it emits a photon of a specific wavelength, and that is what we were looking at earlier.
You'll see a whole series of lines as it goes through the different energy states of the hydrogen.
I should be giving you the microphone here. But no, he is exactly correct. As the electron, to repeat what he said, as the electron falls down through different energy states, it emits a photon of a specific known energy wavelength or color. So that is, we can look at that in the lab and we can compare that to what we observe in the universe to identify hydrogen elsewhere in the universe. And hydrogen is very abundant. Yeah.
On a less serious note, where may the aliens be hiding out?
Later. Other questions? Yeah.
What's the fastest calculation of anything moving away from us?
They don't really talk about, the Doppler shift, you mean?
What's the fastest?
The Doppler, just strictly Doppler shift, a few percent the speed of light, strictly Doppler shift. But when you're looking at distant things in the universe, they weren't moving that fast away from us when the light was emitted. Their light is stretched not by Doppler shift, but the expansion of space itself. It's called a cosmological redshift. The cosmic microwave background, things that from that era, they'd be moving away from us at a large fraction of the speed of light these days. But their light hasn't gotten to us, so we can't see them.
The visitor's going to want to have something concrete compared to faster than a speeding jet.
The universe. Okay, let me talk. I will answer that really quickly, and then I'll finish it. Okay, this gets to an important point between the Doppler effect, Doppler shift, and the cosmological redshift. The Doppler shift, no object can move away from us faster than the speed of light. Okay, so if something's moving away from us close to the speed of light, the light will be stretched incredibly, just like an object moving away from very fast. Its sound would sound low frequency. Well, the space can expand faster than the speed of light. Okay, space can expand at any speed. It doesn't matter because it's not an object moving away from us. It's the space itself expanding. It's completely consistent with Einstein's theory of relativity, and space can expand faster than the speed of light. So yes, someday we're not going to be able to see that cosmic microwave background. Someday the universe will have expanded so much and be expanding so fast that light from these objects cannot get to us. In a sense, we live in a privileged time in the history of the universe because trillions of years from now, people won't be able to reconstruct, if we're still around, the history of the universe because many of these things will have gone beyond the edge of the observable universe as the universe expands faster and faster, exceeding the speed of light. That's kind of how it works. There will be things from which the light's emitting toward us, but the space is expanding too fast for that light to ever get to us.
But the question was, what is the fastest known thing that's expanding?
The fastest thing that's known expanding? Or the fastest thing in the universe? Okay, well, the fastest known objects in the universe, other than light, which travels at the speed of light, would be cosmic rays, which are very energetic protons or nuclei of helium. These cosmic rays can travel at 99.99999, something like that, like percent the speed of light.
25%.
Okay. I don't know because that redshift doesn't tell you directly how fast that quasar is moving away from us. Just because the light's been stretched 25% doesn't mean it's moving away from you at 25% speed of light. The primary part of that redshift is cosmological redshift caused by the expansion of space. Nearby, it's Doppler shift, but when you get far out in space, it's mostly the expansion of space itself stretching the light that's causing that redshift. And I don't know directly how to calculate how fast that's moving away from us today, but you can.
I'm going to tell my business that there are things that are ground?
I really need to move this on. I'm happy to answer your question, but let's get onto the cart and we can talk face to face. Okay, sound good? All right. Thank you everyone for your time. And, let me pass it back to Andy.